Sorry, it was giving me a funny message. When I pause weird, it's because I'm getting stuff on my end. I just don't want it to screw up today on the recording. Okay, so remember that I'm collecting homework as we go now because you're gonna turn it in Canvas under the section, and the 5.1 homework is tonight. And also remember that I'm doing homework help sessions because the tutor centers are closed and it's hard to get together with people, and just to offer you an additional resource because I want everybody to be able to finish this class strong and, you know, get this credit out of the way. So I hold them Tuesday mornings at 10 a.m. in WebEx here, and Thursday evenings at 7 p.m. And I just plan on being on there for an hour or so, depending on how many questions there are or how many things people want to work. If nobody shows up, which nobody did Thursday night, but that's fine. If nobody had questions, that's fine. I'll usually stay for 15 to 20 minutes, and if nobody has showed up in that time, then I will leave. Now, if you want to get help but you can't get there till a little later, if you send me a message or something, I will definitely be there. I want to help you guys. So I want you guys to learn this material and pass the course and be able to move on with your schooling. And so I'm just offering those as help, and you don't have to come if you got your homework figured out. You don't have any questions, that's fine. And if neither of those times work for you, but you have some questions, if you let me know, I'm happy to figure out a time to meet with you in WebEx like an office time and help you. So please let me help you if there's things I can help you with. The test analysis is also due today. I have the tests here, but I don't have a way to give them back to you yet, and so I put in there in that announcement of how we were changing stuff. It's posted on the home page under a link there, but anyway, so I just had to do something different for those. And I have hopes of before the semester's end being able to get the stuff I have for you back to you. The homework from chapters 3 and 4, the ones I collected, I still had them in a stack here because I was going to wait till I got the others. Anyway, today later I will get those scores entered, and then I will just be holding on to it here until we figure out a way to get stuff back to you. So that's kind of the logistics of what's going on. Any other questions? And feel free to just unmute your mic and interrupt me, or type me a chat if you have. I'd prefer the unmute mic and interrupt me because it's faster, but if you don't have a mic and you need to chat, have a question or something, feel free to chat. Type down in the bottom right-hand corner where the chat is, and I can answer your question. So, anything else before we get back to?
I have a question.
Okay, go ahead.
So I still have my homework from the previous section. How do I turn that in?
Okay, so what I've had everybody do for chapters 3 and 4, because this just got hard right here, is I just asked anybody that hadn't turned it in, because I told you you could turn it in that next Monday after spring break that we never had. So you just need to send me your completed cover sheet for 3 and 4. You can just attach it to an email if you want. And basically what I'm doing on chapter 3 and 4 is just taking that cover sheet, and then I will get everything recorded. Got to get it by today, though, so send it to me today.
All right.
Anybody else? Any other questions before we get moving here? Okay, so we're going to hopefully finish our linear algebra chapter today. There's a fair amount of stuff. If we don't quite get through it, it'll spill over to Wednesday just a little bit, and then we'll be ready to start chapter 6, which is back to some differential equations, but some systems of differential equations. So last time we were doing the properties of linear transformations, and we talked about the one-to-one or injective and onto or surjective, and those were just some terminology from linear algebra, and then we were asked some questions about them. We're not going to be using probably those words in tying into differential equations, but then the other thing that we did a little bit of this section last time, so we looked at some linear transformation, just figured out what it would be for a general vector here, And we saw that when we transformed just a generalized vector v1, v2, what we got, and then we expressed it as these two other vectors in a linear combination. And since you got two vectors, but there are three component vectors, this is in R3, and it's building a plane in R3. So we had done that, and then we also, let me get the rest of this stuff on there because this is just a recap where we were. We took a matrix that could be a transformation matrix then, and we got the REF of it, and we learned about what was called the column space. You look for the pivot columns, which are, when it's an REF, the leading ones. So I boxed those in. Then you go back and find those columns in A, and those columns build the image. So it's a way to find what the image of a transformation is by getting the REF of the matrix and then going back to the original columns of A and seeing what the span is. And when we got that, we got 1 and -3 the first column, and then 2, -5 the third column. But since you're in R2 and you got two linearly independent vectors, it'll build all of R2. It'll span all of R2. So you could use those, or you could just use some simple ones, is what we talked about. A couple vocabulary, other things. Then as we learned, the rank was the number of pivot columns, the dimension of the image. They were all kind of the same thing. Actually, I forgot the image theorem here was first. But we went over these theorems. There's the rank. And then the rank is just the dimension of the image. So how many vectors, linearly independent vectors, it takes to build the image. And one way you can find it with the matrix transformation was that get it in REF. How many leading ones are there in the REF? How many rows, start out with the leading one, and that's the rank or the dimension of the image. We also had, this was right out of your book, just saying all these things are equivalent then. The image is the column space of A, and the rank's the dimension of the image, so it's the dimension of the column space, which is the number of pivot columns. So all those things kind of tied in together. And then we looked at one more transformation where we found the image and the rank. Okay, so that's what we did last time on this section. Now we're going to continue on and talk about what is called the kernel. It's also called the null space of a linear transformation. So you're transforming from you're transforming T, and it's a matrix transformation that we're looking at. Well, it doesn't have to be a matrix transformation. It can be any kind of linear transformation. But the kernel is basically the stuff that gets mapped to the zero vector. So you got two vector spaces. Vector space B you're mapping from, and vector space W you're mapping to by some kind of a linear transformation. And so in vector space W, the one you're mapping to, there needs to be a zero vector because these are vector spaces. Okay, the zero vector would look different depending on what your vector space was. But anyway, the kernel is the pre-image or all the stuff in Z that when you apply the transformation, get mapped to zero. So kind of to try and get a picture, here's zero living over here. And remember, zero is not the number zero. It could be, if we were looking at 2 by 2 matrices as the vector space, it would be a 2 by 2 matrix of all zeros. Or if we were looking at linear function, then it would be the function zero. So just equaling zero. Now the kernel then is all the stuff in the first vector space when you apply the transformation ends up equaling the zero vector. Now, notice when I drew it, it's going to include the zero vector over in the first vector space. And this is a linear transformation. So 0 is going to get mapped to 0. But there could be other stuff in the kernel as well. And this is going to be important to figure out. This is the linear algebra vocabulary for solving a homogeneous piece of a differential equation, because a homogeneous equation is when that differential equation equals 0. So it's like if I apply the linear transformation of doing these derivatives and stuff, the kernel is what gets mapped to 0, so it's basically the solutions to the homogeneous equation, because it's what things got mapped. You make that equal 0. So anyway, that's the definition, and there it is in math words, kind of how we write down what the kernel is. Okay, and so it just reminds me of popcorn, even though, I don't know why. So I just put the word pop in there to say, if you're going, what's the kernel? Oh, popcorn. Oh, yeah, that 0 in the middle. It's the stuff that's the O in the middle, but stuff that gets mapped to 0. So whatever. Okay, so let's find out how to find the kernel by looking at an example here. All right, so first of all, let's fill in the blank. I'm transforming from some vector space to some other vector space, and you should be able to answer these questions, fill in this blank, because you can see what kind of vectors you are going to transform, and then you can see what they look like after they're transformed. So what goes in the first blank? What vector space am I transforming from? So like our normal vector space V, what is it?
R3.
Thank you. Yes, it is. The reason I know it's R3 is because there's 3 component vectors that get transformed. Okay, and what vector space am I mapping to? Okay, I heard 2, and I got in the chat 2, and the answer is no. You'd think it's 2 because it looks like a 2-dimensional thing. It is a 2-dimensional thing because of the 0. But the actual space it's mapping to has 3 components to it. So because the vector transformed has 3 components, I am mapping to R3. It's not going to be onto or surjective, meaning it's not going to cover all of R3 because the Z is always 0. So I will be mapping to a plane in R3, a 2-dimensional thing in R3. But I am mapping to R3 because the transformed things have 3 components. Okay, I don't want to write in red, so let me change that. All right, so now we're going to ask the question, what is the kernel of the transformation? So let's kind of, oh, no, I don't want to see that yet. I have a visual. I thought the visual was first. Okay, so give me a vector that would map to the kernel. And the kernel would be what gets mapped to 0, 0, 0 in this second space. So is there just one thing that gets mapped? Just 0, 0, 0 gets mapped to 0, 0, 0, or are there other things? Okay, thanks, Jacob. Jacob says 0, 0, 5. Actually, if we had x being 0 and y being 0 and have, so this is what he said, 0, 0, 5, sorry, will get mapped to 0, 0, 0. And that would work because you would put the x in there, which is 0, put the y in there, which is 0, and then in the mapping, you always make the z 0. So that would work. So the kernel would actually be anything that has 0 for x and 0 for y, so that they'll be 0 when you get them mapped. And z could be anything, because whatever it is, you're going to put 0 in the transformation piece. So this would be the kernel, and there's my picture I thought I'd had first. So mapping from R3 to R3. And we want to know what gets mapped to 0, 0, 0, and we're going to map a line, basically the z-axis in R3, because z can take on anything, and it will get mapped over here to 0, 0, 0. So that's what the kernel is, and like I said, the reason we're learning about it is because you can think of it as also a solution to the homogeneous piece of a differential equation, because when is the differential equation 0? So trying to give us an idea of why we're learning it. Any questions on that? Okay, let's look at a matrix transformation, and let's figure out what space we're mapping from and what space we're mapping to. This one's the one you got to think about. If you were going to take a vector v right here, how big would it need to be? Let me try and make not necessarily the same. How big would it have to be so that I could do the multiplication? So what's the original space? What's the size of the original vectors that I could transform with this? Anybody? How big would it have to be? So matrix multiplication, you go across the rows and down the columns. So how big would it have to be?
3 by 1.
Okay. So we're going to be in R3 then, because if I wanted to be able to multiply this, I've got to have this, when I go across this row, I've got to be able to have the same amount going down this column. So I'm going to map from R3. What is the vector space I'm going to map to by multiplying by this matrix? Somebody can answer? Go ahead. If I did the matrix multiplication, I go V1 plus V2 plus 2V3, and that would give me the first component because I go across the row and down the column. Now I got to go across the second row and down the column. So that's 2V1 plus 3V2 plus 5V3. Well, I just got a 2-component vector. So this is going to map vectors to R2. Because when I multiply it by the matrix, I take a 3-component vector, I do the multiplication, I get a 2-component vector. So this is going to map then to R2. Okay? So I put that in there, but I'm erasing it. And the reason I'm erasing it is because something else is going to show up there, and I just wanted to show you that. Okay, so we want to know what is the kernel of the transformation. So basically, what I'm asking you is when I put in this vector V1, V2, V3, and I do the multiplication, which ones would map to 0, 0, which is the 0 vector in our codomain where we're mapping to. So that's what we want to know when they ask the question, where is the kernel? So let's do, I erased it, I should have left it there. Let's do the matrix multiplication, and we're going to get 2 equations. So I'm going to go across the row and down the column, V1 plus V2 plus 2V3. And that has to equal this first guy, so that has to equal 0. And then we can do the second one. Make sure mics are muted. We're getting some background noise, so can I get you to just mute your mic? You click on the over by your name. Thank you. All right, so 2V1 plus 3V2 plus 5V3 has to also equal 0. So that's kind of the requirements to find the kernel. If I could solve this system of equations, I would have the kernel. Well, guess what? That's why we learned Chapter 3. We solve systems of equations because we need them for things like this. So let's put it in a matrix, 1, 1, 2, 0, and 2, 3, 5, 0. And let's do row operations so that we can get this in REF. And in fact, I want it in RREF. And then I will be able to write down what the kernel is. And I've only got 2 equations and 3 variables, so I already know right now the kernel is more than the 0 vector. Obviously, the 0 vector works. If all of these were zeros, it's 0. But there's going to be more than that will work because I don't have enough equations to determine a unique solution. All right, so let's do, I'll put it down here, the REF. RREF. So we'll leave row 1 alone for a minute. And then we'll do -2 row 1 plus row 2. So -2 times 1 added to 2 is 0. -2 times 1 is -3 added to 3 is 1. -2 times 2 is -4 added to 5 is 1. And then the zeros obviously stay 0. All right, so now that I have that, I'm in REF, but I'm going to get RREF, and so I want this guy to be a 0. So I'm going to use the second row added to that one to be able to get that 0 I need. I'll subtract it. So I'm going to take row 1 minus row 2. That'll give me 1. 1 minus 1 is 0. 2 minus 1 is 1. And still have the 0. And then 0, 1, 1, 0. Okay, so we learned the R and RREF in Chapter 3 because we've got to be able to do it to find kernels, and we also got to be able to do it to find eigenvalues and vectors, which is our 5.3 stuff. All right, so remember how we did that. This is V1 column, this is V2, this is V3. We first identify what variables are free, and variables that are free are the variables that do not have a leading one. This is a leading one, this is a leading one, because they lead off the row with it, but those are the two leading ones. So we still have another variable that's a free variable, and that's V3. So V3 is free to be anything, so we give it a parameter, I'm going to call it T. So then V2 is, if we put the variables back in, this would be V2 plus V3 equals 0. So if we solve that for V2, it'd be minus V3, which is minus T. And then back to the first row, same thing's going to happen. V1 plus V3 equals 0. So moving it over and, putting in the parameter, I don't know why my pen did that. That's also, let's fix that. That's also negative T. So, anything T could be anything. You pick 0 and it maps to 0. You pick 1, so I'd have negative 1, negative 1, 1. That would map to 0, 0. Now, the way we're going to write the kernel then is we're going to, typically we would factor the T out in front because we just want a vector that'll build the kernel. And so that's going to be negative 1, negative 1, and 1. So the kernel is going to be built by taking scalar multiples of negative 1, 1, 1. If you put negative 1, 1, 1 in here and you did the matrix multiplication, you're going to get 0, 0. And if you put in 5, 5, negative 5, that would do it as well because that would just be negative 5 times this. So that is the kernel. So if I was describing the kernel, I would say it is a line in R3. It comes from the original vector space, and so it's in R3. You can see it has 3 components, but just taking scalar multiples of one vector builds a line. So I wrote here, and I got all this stuff to go over the top of it. I should have duplicated this slide. Actually, give me a, well, no, that's all right. Well, yeah. No, I want to keep them. I was going to go out here and try and put this in one more time because I've got all that stuff over the top. So let me just do that. I've been trying to plan ahead and put in slides so that I don't have to do this, but I didn't think about it on this one. So now when I print the annotations for the slides, you should be able to see one that has the annotations and then one that has me. Oh, don't tell me because I say that's not going to let me erase it. Not going to let me erase it. I'll learn from this. I just learned something. Okay, so we found the kernel, and this is over the top, so sorry. It's kind of crazy. I'll put it down here. This is just how it was written in the book. Now, is that the same thing as we got up here? And it is, because we use T instead of C, doesn't matter. And we had negative 1, negative 1, 1, but that's a scalar multiple of, if you multiplied ours by negative 1, you would get theirs. So, just 2 different ways to list it. So that's fine. And these are going to be over the top. Like I said, I will plan next time a little better for this. So we started in R3, and we mapped to R2. And we were interested in what mapped to 0, 0 in R2, and we found it was a line in R3, a line that contains the vector 1, 1, negative 1. So everything along that line gets mapped there. So that's a good illustration of how to find the kernel and kind of get a better sense of what the kernel is. So any questions on that one? Okay, sorry, that slide was a mess. All right, so now we're going to look at kernels of different sizes. Okay, so we're going to find the kernel of these different transformations here. We got 3 different examples. So let's start with A. I don't want red. Okay, so if we want to find the kernel of A, we take A and we augment it with zeros, because basically we're going to be finding anything that gets mapped to have it equal 0 then. And we're mapping all of these, we're going to be mapping from R2 to R2, because it takes 2 component vectors to be able to multiply, and then you're going to get 2 component vectors. Okay, so let's do the RREF of this one. And so I'm going to take, actually, because I want RREF, I'm going to do something different here. Because these guys match up right now, I'm going to take, no, I don't want to do that because that'll mess up the front. Sorry. I'm just going to do -4 row 2 plus row 1. So I'm going to leave row 1 alone. And then I'm going to do -4 times it added to row 2, and that'll give me 0. -4 times that's -4. Plus 1 is -3 and 0. And so then if I did one more time, I'm going to do -1/3 row 2 would give me 0, 1, and 0. And so if I wanted the RREF, I could now use my new row right here and take row 1 and subtract it. So I'm going to write it on this side because I'm doing it in the same step to save. So it's this new row 2. I say, actually, that's what I'm going to put up. I'll put it right here. So row 1 minus row 2. The old row 1 minus row 2 over here. So 1 minus 0 is 1. 1 minus 1 is 0, and 0 minus 0 is 0. So what happened when I did the RREF is I got an identity matrix there, and that tells me the solutions. V2 is 0. And V1 is 0. So the kernel of this transformation is only the 0 vector. 0, 0 gets mapped to 0, 0, and it's the only thing that does. So we say the kernel's dimension is 0, since it's just a point that gets mapped. So kernel has a dimension of 0, and it's this transformation, yes, the kernel is, and it's just a point. I said that right. Okay. Now let's look at B. Let's do B in a different color so it kind of contrasts a little bit. So we're going to take matrix B, which is 2, 1, 0, and 2, 1, 0. And this one's going to be easy to see what's going on with REF. If I subtracted the rows, I get zeros because they're the same. And then I'm going to do 1/2 row 1, give me 1, 1/2, and 0. Okay, so I have a free variable. Here's V1 and here's V2, and there's only a leading one in the V1 column. So V2 is free to be whatever. We're going to call it T. And V1 then, if we put the variables back in and moved over, would be -1/2 T. And here is a trick that we're going to be doing with Eigenvectors as well in the next section. So I'm going to just show it to you now. Rather than have fractions in the vector you use as your building block, you typically factor the fractions out, just because it's harder to work with a vector with fractions than work with a vector that's not. And any scalar multiple of this will work and be a building block, so we want one that doesn't have fractions. So I'm going to factor out a -1/2 T out of both. What that does to the first one is it leaves a 1, which is going to make it easier to work with. How do you factor a -1/2 T out of T? Well, the t's out there, and you need to put whatever here so that when you multiply it by negative half, you'll get the t. So negative 1/2 t times negative 2 is, 2 over 2t or 1. So this is what we're going to use. If you would have use it like we saw it here and not factored out negative half and have negative half and 1, it's not wrong. It's hard to work with, and we're going to want to be working with them. So we're going to factor any fractions out as well, because we just need a building block to build the kernel. The kernel is made of all scalar multiples of the vector 1, negative 2. So this is a kernel with one dimension, a line in R2 that gets mapped to 0, 0. All right? Then we've got C to work with, and C is the last one, and it seems like kind of a weird one, but it's just so we can make a point here and kind of understand that different things could happen. If you started out with 0, 0, 0, you got 0, 0, that's weird. So the kernel is the whole space, because any vector you pick in R2, if you multiply it by matrix C, it's going to get mapped to 0, because it's just going to zero them out, and they'll all be zeros. So this was a 0-dimensional kernel. This was a 1-dimensional kernel. I don't know why my pen's doing weird lines like that. And this one is a 2-dimensional, or the whole space kernel. So they could end up being different sizes depending on what your transformation matrix is. Okay, and now that I've shown you that, I am going to have to erase this slide. I'll plan better first next time on duplicating slides, because I got to show you a couple more things on this slide, and I want to get all this stuff out of the way. I'm learning how to do this and write on the slides and have it, so I've duplicated some of them so I didn't have to do this, but I can see the ones I missed. All right, and if I pull out, then I lose what I have, and I want the other stuff, so I'm just going to have to erase. Like I'm erasing the board. Okay. Oh, let's see. Where'd it go? Oh, I did. Dumb. I didn't need to erase that. That's all right. This was on the old slide originally, but I made it bigger and put it on its own slide and forgot I'd already fixed this one. Okay, so Kernel Theorem. So if we have this linear transformation from V to W, there's two things in the kernel theorem. The kernel is a subspace of V. Remember, a subspace is a vector space itself, so it's a subspace of the original space. And T is injective. Injective means one-to-one if and only if the kernel is 0, or a zero-dimensional thing. So it just makes sense. It's just saying to be one-to-one, you can only map one thing to one thing, and 0 would get mapped to 0. But if the kernel is anything more than just 0, then more things are going to get mapped to one thing, and it won't be injective, which is one-to-one. Okay? And one more vocabulary word. The dimension of the kernel is called the nullity. They also sometimes call the kernel the null space. Null means 0. So if they say, what's the nullity of this transformation? They're asking you, what's the dimension of the stuff that gets mapped to 0? All right, so let's go ahead now and see how we might use this stuff. So are we getting an idea of the mapping? Can you help me fill in the blanks? Oh, I got a question. Sorry, I should have looked. So the matrix has linearly independent values. It will always end up as a matrix of 0. If it had a unique solution, then it will always. So because they were 2 by 2s, in answer to your question, Jacob, because they were 2 by 2 matrices, that's going to be true, because you can, if you've got just 2 by 2s, you can always look at one and see if it's linearly independent from the other row, and if it is, then you know that you're just going to get 1, 0, 0, 1 when you do the operations. Now, if you had R3 or something bigger, you can't tell by looking at it, because you could add 2 together to get a third and not be able to see that in your head. So the answer to your question, it was a good one, is yes, if it's a 2 by 2. Okay? But, yes.
I also have a question.
Okay, go ahead.
On the previous slides, on the B, was that similar to the, one of the test questions that we had on the last test?
Okay, B. Okay.
Yeah, I remember, like, it was like the first question. The way you approached it, would that be the way that you would approach the problem on the test?
The one where they asked if they were bases for R2, or which one are you talking about on the test? Let me grab the test.
Maybe we can talk after class.
Okay. All right. Yeah, I'm happy to do that. So let's be sure and do that. Okay. All right. Anything else? All right. Can you help me fill in the blanks here? So what vector space would I be mapping from? Okay. Got Benjamin and we got Colton both telling me R4 to R2. So let's see. R4. Yes, because I got to go across the row and there's 4 components. So that means my vector over here has to have 4 components. I only got 2 rows to go across. So I'm going to be mapping to R2. Good. All right. So now what we're going to want to find is the kernel and the nullity. Remember, the kernel is what gets mapped to 0, and the nullity is the dimension of that stuff that gets mapped to 0. So let's go ahead and do that. So I want to give you an example so you can make sense of all this. So we're going to take our matrix, and we are going to map it to 0, 0. Actually, Jacob, here's a good one to look at. There's only 2 vectors, and they are not multiples of each other, but because it's not a 2 by 2, you know, we've got 2 rows and 4 columns, there is going to be dependency here. So that's why I was saying in the 2 by 2 case, you can look at them, and if one's not a multiple of the other, then what you said was true. Okay, so let's go ahead and get the REF of this. And actually, I'm just going to do row 1 minus row 2, because that'll give me a 1. So 2 minus 1 is 1, negative 4. Actually, I'm just adding those. I put minus, but I'm just adding them. 2 minus 1 is 2, negative 4, and 2 is negative 2. Just adding these up, that's a 1. The next one's a 3, and then I got a 0. Okay. Now, let's see. Now this would work, but you have to be careful because I've only got the 2 rows. I'm afraid that's going to mix me up in the end, so I'm changing my mind. Sorry. I decided that was going to end up causing you to do something you don't want to do. So what I'm going to do instead to get the leading 1, I'm trying to avoid fractions, so I'm going to trade rows places. But after I trade the rows places, well, let me just trade them first so we can do it step at a time. I decided the other way is going to cause you sometimes to make some mistakes, so I'm going with the more straightforward way. So I'm trading rows places. I'll leave this row alone. The pen is acting up today. Okay, and then I am going to go through that first row with a negative 1. I'm going to do that right now because then I can save me space here. Okay, what I was doing there was getting my leading 1 that I wanted. Okay, and now that I have that, the next step, I'm going to use it to 0 out below it. So I'm going to keep the first row alone. 1, negative 2, 2, 3, and 0. And then I'm going to do negative 2 row 1 added to row 2. So negative 2 times that added to 2 is 0. Negative 2 times negative 2 is 4. Minus 4 is 0. Negative 2 times 2 is negative, let's see, so let's try it. Negative 2 times 2 is negative 4, added to 3 is negative 1. Negative 2 times 3 is negative 6. Added to 6 is 0. Okay, so that's what I get. All right, well, I'm trying to get the RES, or in fact, I want the RRES. So the next thing I'm going to do, and I'm going to do it in the same matrix here, is I'm going to do negative row 2. Times it through by negative row 1, and that'll just change the sign of that. I now have the leading ones, but I want to use this one here in the second row to zero out above it, and then I will have the RREF, and then I'm going to be ready to figure it out from there. So what I'm going to do is I'm going to take row 1 minus 2 times row 2. Okay, so that's going to stay a 1, that's going to stay a negative 2. Minus 2 times that 1 is minus 2, added to 2 is 0, and then the other guys are going to stay, whoops, I put the line in the wrong place. The other guys are going to stay the same. So this is just back to chapter 3, elementary row operations to get our REF. And now let's go ahead and see if we're going to be able to tell what the kernel is then. This is V1. This is V2, this is V3, this is V4. They're just components of my vector. And these guys have leading ones, so they are the bound variables. But it looks like V4 is a free variable, so we'll call it T. And V2 is a free variable, so we'll call it F. And actually okay, that's fine. Okay, so now V3. Here's V3. V3 is 0, because if you put the variables back in, you just have V3 equals 0. V1 is 2V2, so 2S minus 3T, because if you put these in and you move those to the other side, if you have it equal to 0, move those over. All right, so let's go ahead and write down then what our kernel is. We just found it, but let's write it in an easier sense with vectors. I'm going to factor the S out of the vector for the first piece and the T out for the second piece. Since there's no fractions, I don't have to worry about that. I just factor out the S and the T. So if I factored an S out, I would have 2, 1, no S's in that, no S's in that one. Now looking at the T's, factoring that out, I'd have negative 3, no T's, and 1. So what I just wrote down is the complete kernel. It's built from 2 4-component vectors, 2 of those vectors there. And so if I were to answer the question, what is the kernel? Well, I could write a basis for the kernel. I would just put in these 2 vectors if I wanted a basis. Or I could write it like I did it here. This has those in a linear combination. So either one of these, the kernel is either the span of what I'm writing now, or you could write it is this linear combination. Either way will express the kernel. Now what is the nullity? The nullity of this is 2, because it takes 2 vectors to build the kernel. Okay, any question on anything I did? Because this is a really good example of what you're going to need to be able to do, which is find the kernel and give the nullity. And so, any questions on that? Okay. If there's no questions, let's go ahead then and kind of connect this to differential equations. This is a bunch of notation, a kernel of a differential operator. So they typically will use L because it's a linear transformation, and it's going to match from continuous functions is what C is. With a little n above it, it means they have n continuous derivatives as well. So you know they're all differentiable. So it's a collection of all the continuous functions whose have first, second, third, up to nth derivatives are also continuous functions. And when you take an nth derivative of a continuous function, you're going to get a continuous function. So it's going to map to C. So that's just explaining sort of this notation. And if you apply it to Y, this is called a linear operator. And you apply it to Y, and you get this generic form of an nth order differential equation. So let's look at it specifically. Let's look at it for a second order, just this one specifically. Okay, so if we wanted to know, first of all, how to express this differential equation in terms of this linear differential operator, this is how you would write it. Because it's second order, you would have a 2 here. You would be mapping to continuous functions that have 2 derivatives that are continuous. You'd be mapping them to continuous functions, and the way you would be mapping them is you would take the second derivative of the function and you would add it to the function. So it's a differential equation, but thinking of it in terms of a transformation. Okay, so we're going to ask, what is the kernel and the nullity of this transformation? And so the kernel is what gets mapped to 0. So it is the solution to this differential equation, the homogeneous solution. So in other words, we want to know the kernel. It is when this equals 0, which is what the homogeneous solution is. All right? So how would you solve that differential equation that I just wrote down? We had ways to solve it. Or you can remember it from stuff we did in the first part of chapter 4. I'm just going to use a characteristic polynomial to solve it. So R is plus or minus I. And then if you remember when we had complex roots, basically we had e to the 0t here because there is no real term right here, and then we would have sine of t plus I sine of t, and oops, sorry, I did that wrong. This is cosine. Cosine of t plus I sine of t, but picking off, we know both the real and the imaginary parts solved it, and so the kernel is built from cosine t and sine t. So this is just back to solving a basic homogeneous differential equation that we had. The kernel is the span of this. This was the basis for the kernel. So anything you can build with the building blocks of cosine t and sine t in a linear combination is in the kernel. So what is the nullity? The nullity would be 2 because you have 2 building blocks that are linearly independent. So the kernel is a 2-dimensional subspace of our original space here of C2. Okay? So basically, and I've got stuff written here. Oh, I didn't have it on here. Okay. So you can see that when we ask for the kernel, applying it to a differential equation, the same thing as saying what's the solution to the homogeneous differential equation. Same thing. All right. So let's look at another differential equation here. And let's see, we wrote down that official notation for linear operator. We're going to be mapping from continuous functions with first derivatives continuous to continuous functions, and we're going to do that by doing y prime plus y. And so we're going to ask that same question, what's the kernel and what is the nullity? And so I could write down, we could maybe remember, but even now that we know this, we can actually, even for first order, we had other ways of solving first order, but I'm interested in where this equals 0 to find the kernel. And so I can just write down the characteristic equation, and that means r equal -1. We had other ways to solve this. We had the integrating factor and et cetera, but you can also find it this way on this particular one. And so e to the -t would be what I would get to build the kernel. So the span of this, or linear combinations of this, which would just be my scalar multiple, this would be the kernel. Now, if we wanted to know the nullity then, because there's one building block, the nullity is 1. Okay, so, all right. So, is there any questions? This is kind of connecting this to differential equations a little bit. And we got a couple more things then to talk about on this. Oh, that was what I said about the homogeneous. The dimension theorem. You're mapping a linear transformation from V to W from a finite vector space V, then finite means it has a dimension, so it's R2 or it's R5 or it's C3 or whatever. The nullity, which is the dimension of the kernel, plus the rank, which was, remember to find the rank as looking at the image, is going to equal the original space's dimension. So let's look at a picture of what this says. It basically says if you have the kernel and you're going to be mapping things over to the image, the kernel stuff is going to get mapped to 0, and then all the other stuff in the vector space gets mapped to other stuff. And so the pink that I have here is the image. So all of these other things got mapped over here in some way to, oh, sorry, I got to get them into the image. They don't hit all of the things. This is not surjective or onto, because there's these little vectors that live around in here that didn't have a pre-image. So the image is there. So what this is telling us, if we take the nullity, that's the dimension of this, dimension of the kernel, and we add it to the rank, and the rank was the dimension of the image, so maybe I'll just put that right here, dimension of the kernel plus dimension of the image is going to equal the dimension of the original vector space. And that sometimes can be useful because it can help us figure out, you know, if I knew the original vector space dimension and I knew the rank or how, you know, what the image dimension of the image was, then I would know the dimension of the kernel, because I could take the original space minus the rank and I would have the nullity. So just a good thing to know is this piece right here, and we'll be able to see it in action in a minute. Okay, so for this transformation, we're going to use this transformation matrix. And I'm hoping you guys are going to look at these and just answer me really quick now, where we're mapping from and to, because I want you to get a sense of what these are. So we're mapping from, obviously it's going to be R3, because there are 3 rows. Okay. And then we're going to map to R2 because, sorry, I just said 3 rows. That's not right. There's 3 columns. If we go across the row, we need 3 things to get across the row. And then there are 2 rows to use, so we're going to be mapping to R2. Okay? So we want to find the kernel, the image, the nullity, and the rank. So basically, on this slide, I'm going to cover everything we needed to get out of this section. Okay? So, how do we go about doing that? Well, first we're going to find the kernel. So, let's go ahead and do that. So how do we find the kernel? We take this thing and we augment it with 0. We're figuring out what got mapped to 0. So we'll put this in right here. And we're going to get the REF of it. I've done that quite a bit in order to save time. I'm just going to write down for you what the REF is. It's just those row operations. Whoops, hold on. Okay. One more out of the way. Okay. So I would get 1, 0, 1/4, and 0 when I do these row operations. If you're struggling with row operations and want some extra help, stay after or tomorrow. Sorry about the phone. And I can help you with them. But you got to be able to get things in our REF so that we can answer this. So first of all, I'm trying to find the kernel. And I can see then that I have a free variable. So I'm going to call V3T. So V2 is negative 1/4 of that. And V1 is also negative 1/4 of that. Okay, I could factor out the T and I could have fractions, but I'm all about making my life easier. And so I'm going to factor out negative 1/4 T. Okay, so then that will leave a 1, and here will be a negative 4 because negative 1/4 times negative 4 would give me the original T that I have there. Okay, so the kernel of the transformation is the span of this vector. There's 2 1s there. It looks like one big long line. No, it doesn't look right. Come on. Sorry, trying to... There. Okay. All right, so we found the kernel, and so we now know the nullity as well. The nullity is 1 because the kernel is built from one vector. The dimension of the kernel is 1. That's the nullity. Okay, so now the other thing we want to do is find the image. Okay, how did we find image? We got to go back to something we talked about last time. That was you build the image by getting the matrix in REF or RREF, and we have an augmented matrix with zeros here, but we already did the work. We could look at this matrix right here. And these two have the leading 1. So they are called the pivot columns. And you go back to the original matrix, and the first one was in the first column, so you use this column. And the second one was in the second column, so you use that column, and that builds the image. So the image of the transformation is the span of it's the column space of A. So it's the span of using 1, 2, and 3, 2. Now, we're in R2, and it takes only 2 to span, so the image is also all of R2. So you could do it either way. You could list the ones I just listed because that's clearly they came from the columns of A. Or you could have even used 1, 0, and 0, 1 when you say, well, it's 2 vectors in R2 to build the whole space. But I
understand that, right? You're saying that the image comes from the pivot columns, so if it was the columns 1 and 2 create the image?
Yes.
Okay, thank you.
Yep, so the pivot columns were in column 1 and column 2 here, so then I went over to the original matrix and I picked off column 1 and column 2. Yep, and that's how you build the image. So the image is 2-dimensional, right, because it takes 2 vectors to build it. Now, we're going to, let's check that last little thing. That last little thing said if you take the nullity, that was 1, plus the dimension of the image, that was 2, it will equal the dimension of the original vector space. And that's true, because the original space was R3. So this theorem back here, nullity plus rank equals dimension of V. That's what I was just verifying here. The nullity is 1, the rank, or the dimension of the image, is 2. They mean the same thing. Add them together, you do get the dimension of the original space. Okay, so that's what that theorem was just telling us. Now, let's determine whether the transformation is injective or surjective. Okay, first of all, is it injective? You're going to need to answer some of these in the homework, so let's make sure we know the words. Injective means 1-to-1. Is it a one-to-one mapping? Anybody? I want these words to start to mean something, so give me a minute to think about it. Do things in the original R3 space get mapped to only one thing in the R2 space? If there's a time you can figure out, or you can figure out that two vectors would get mapped to the same thing in R2, it is not one-to-one or injective.
It would be injective, right?
Well, what was the kernel? The kernel was built with one vector. The kernel is a whole line. So there's a whole line over here that gets mapped over here to 0. Everything on this line does. So do you see why it's not one-to-one? The only time it could be injective, which is one-to-one, is if the kernel was only the 0 vector. Because then 0 would get mapped to 0. If the dimension of the kernel is 0, it's injective. If the dimension of the kernel is anything else, it's not one-to-one because you're mapping all of those things over to 0. So 0 gets hit more than once. Does that make sense, everybody? Okay. Is it surjective? Surjective means onto. Onto means you cover the whole space. So, in other words, when I'm mapping from V to W, does every single thing in W have a preimage? Does it get hit by something? Something over here gets mapped to this one. If I pick something here, does something over here get mapped to it? What's the image look like? Okay. Jacob, you gave me your chat answer, which is good. That's exactly what we're saying. So perfect. Sorry I didn't notice you first. All right. So on the surjective piece, it is surjective because here's the image. I've written down the image up above, right here. The image is built with two vectors. So two vectors that are linearly independent span all of R2. They cover all of R2. So it is surjective. Everyone's going to get hit because the image is all of R2 and the vector space W is R2. So everything is going to have a preimage. All right, any questions? Because that kind of put in that one, gave us a chance to put together a little of everything from this section. Got one more. That's all, and then we'll have a short break, and then we'll get started on 5.3. Okay. Can I fill in the blanks? What space am I mapping from? I'm waiting for somebody to tell me. Okay. Mapping from, I've got a couple of good answers. R2 to R4. That's right, because if you're going across the row, you need two components to do that, to do the multiplication. So we got 4 rows to do it, so we're going to be mapping to R4. Okay, so this is the transformation right here to get from R4 to R2. All right, so first thing is determine the nullity and the rank of the transformation. All right, well, let's go ahead and let's find, I gotta move this window you don't see out of my way so I can write. Okay, so let's go ahead and figure out, I'm just in the interest of space, I'm gonna augment this, okay? So we're gonna find the kernel, so then we're gonna answer the nullity. We're going to find the kernel, and there's no work to do because it's already in our REF, okay? So basically, we've got V1 equals 0 and V2 equals 0. And that's it. So the kernel is just 0, 0. So 0, 0 gets mapped to 0, 0. The nullity is 0 because the only vector that gets mapped to 0, 0 is the 0 vector. All right, well then, what would the rank be? I can use that theorem to answer that, because nullity plus rank equals the dimension of the first space. And so the first space was a 2, so 0 plus 2 is what I would need to equal 2. So this is the rank, or the dimension of the image. And I'm just using that theorem that says nullity plus rank equals dimension of the first space. Dimension of the first space was 2, nullity was 0, so the image must be 2. Okay? Now, what is the image then? I'm mapping to R4. I guess it actually asks, well, yeah, just ask for the rank. It didn't ask me for the image, so that's all it asked me for. Okay? Is it injective? Is it 1-to-1? And the kernel is 0, 0, so the answer is yes, it is. Okay? And is it surjective? So this was yes. Is it surjective? There's no way it can be surjective because you're mapping from a 2-component space to a 4-component space, so everything is not going to get hit. And in fact, when we get the 4 components, if you saw you have these 2 components and you go along, these are going to make some zeros in there, and so you're going to have a lot of things that aren't going to get hit. So the answer is no, because you can't take something with 2s and multiply and get to 4s and be able to have it cover everything. So anyway, that kind of wraps up 5.2, so I just want to give anybody a chance to ask a question about anything that wasn't clear, give you a chance to run to the bathroom, grab a drink, whatever, and then we're going to start our eigenvalue and eigenvectors. Okay, yes, it can be, good question, Gringo, can it be both injective and surjective? And the answer is yes, it could be. This particular one wasn't, but I'll keep those. But let me go back to the very first one, when we first started talking about that, right here. 1-to-1, and okay, and this one was not surjective because the 8 didn't get hit, but this particular one is 1-to-1. Each one only goes to one place, but everything gets hit. So this is an illustration of the injective and surjective. So the answer could be, when I ask is it injective, is it surjective, you could say no, no, yes, no, no, yes, or yes, yes. I mean, it could be any combination, just depends on what you have. Any other questions? Okay. I'm going to have a quick drink of water here, and then I'll pull up the next slide. The next group of slides, I'm going to... Okay. We need to learn how to find what are called eigenvalues and eigenvectors. And that is why we're learning all this stuff, really. To be able to solve systems of differential equations, and kind of all the background stuff in linear algebra leads up to being able to find these values and vectors, which then lets us build solutions to systems. So that's the plan. Everybody hanging in there? Looks like everybody. I didn't want to throw me to the break. I wanted to just give you a couple minutes or two to get back here. All right, I'm going to get started then. So, yeah, we're still talking about linear transformations, and hopefully now everybody's really quick at filling in the blanks. This is going to go from R2 to R2. And when we apply the transformation to various vectors, I want you to visually see what it does. Okay? So here is a transformation. I'm picking the vector 1, 0, and I'm going to transform it. And so how I transform it is I just multiply it by this matrix. And if I multiply it by the matrix across the row, I get 1 and 0, which is 1. And then second row, I get 2 and 0, which is 2. So that's where this came from. I just did the matrix multiplication, and I got the new vector. But let's visually see that. So we started with this vector. U is the original vector, 1, 0. And we're going to look at them as vectors. That's what we want. And so I started at the origin, and I put the tip at 1, 0. But when we transformed it, I got 1, 2. So that's what the transformation looks like. So you see it's rotated around a ways, and it's also scaled. It's longer than it was by applying this transformation. So visually seeing what a matrix does to a vector, there's an example. Okay, let's try transforming a different one. We're going to transform 0, 1. And if you did the multiplication, you get 2, -2. So we still start with U, which is 0, 1 this time. And once it's transformed, we got to go to 2, -2 for the tip, and that's what it looks like. All right, so started with a vector that was 1 long. The last vector was 1 long as well. But this time, it's rotated a different angle, and it's scaled by a different amount, by quite a bit there. Okay, let's take another vector, -1, -1, and let's apply the transformation. So multiply it by the matrix, and let's see what it does. So here's the original vector. Here is the transformation vector. And so we're mapping from R2 to R2, and we see it's changing both the direction and the magnitudes of these vectors. They have a different angle by the time they're transformed, and they also have a different length. Okay, let's look at another one. This particular one, vector 2, 1, when I transform it, I get 4, 2. This one is different than the other ones we've looked at because the direction angle did not change. The scale did change, so it's scaled, it's multiplied, it's actually twice as long as the first one, but the angle didn't change. It turns out then this is an eigenvector. The 2, 1 is an eigenvector, and we're going to officially define it in a minute, but bottom line, this one's a special one because it didn't change the direction angle. Okay, let's try another one. 1, -2, and this is what I got when I applied the transformation, -3, 6. Now, it might look like here the direction angle changed, but I can actually write a vector that is the same direction angle as U if I scale it with a negative. So the new vector I got is -3 times U. It's scaling the original vector, this time by a negative, so it goes up the other way, and it's 3 times as long as the original. This is also an eigenvector then. So eigenvectors are special vectors of a transformation that when you apply the transformation doesn't change the direction angle, it just scales the vector. The one we saw a minute ago scaled it by 2, this one scaled it by -3. So here's the official definition. If you have a transformation going from one vector space to another space of the same vector space, it's a linear transformation. The scalar, this is the Greek letter lambda. If you're not used to that or didn't know its name, we're going to be talking about lambdas right and left here in this section and then also in chapter 6. So they use lambda to stand for the eigenvalue. Okay, and it is when you find the special vector that when you transform it, it just scales the vector. It doesn't change the direction. It just multiplies by a scalar. That scalar that it multiplies by was the eigenvalue. And the special vector that has that property is called the eigenvector. And so, and the eigenvectors are non-zero. The zero vector would make this equation here in the middle true. You transformed a zero vector, you'd get 0, but that's not an eigenvector. It has to be non-zero. Okay, so basically, if we were multiplying, look down at the bottom, if we were multiplying by a matrix A, and what it did was it just scaled it, so we could have just multiplied it by a scalar and got the same answer, then you know that you have an eigenvector. That is an eigenvector. And lambda, the amount it got scaled by, is the eigenvalue. All right? So we're going to be working with that and seeing if we can make some sense of how to find those, and we'll be able to do that. So let me go to this next slide. So this is what has to be true to have an eigenvector. It has to be true that if you would have multiplied it by that matrix, it would got the same answer as if I would have just multiplied it by a certain scalar. All right, so we're going to take this, and the first thing I'm going to do is I'm going to move it to the other side. So I'm going to take this, subtract the lambda v. Now this other side is not 0, it's the 0, it's a 0 matrix or vector. Actually, hold on. Before I can actually subtract it, I got to do something else. Sorry. I want to actually take this and put the identity matrix in here and have the identity matrix be the same size as A. The reason I need to do that is because I want to be able to subtract these matrices, and they need to be the same size to subtract them. That's why I had to put it in there. Let me write out what this means. This means, well, I guess I can't write it till I have a size. We'll be writing it in a minute. But I stands for the identity matrix, and it's the same size as whatever A is. So now, when I move these over, like I was going to do, it makes sense that I can actually subtract them. They have to be the same size to subtract them. And when I subtract them, I will then get the 0 matrix that's the same size as A, because I subtract first component and first component, and because they were equal to each other, when I moved it over, they're just going to cancel each other out. All right, now the next thing I'm going to do is I'm going to factor out the V. But when I factor out the V, I'm going to write it on the end instead of in the front, like that. Just because that's going to make it easier to work with what we want to do here. All right, now we got to think of this for a minute. Stuff we learned back in Chapter 3. Okay, something we learned back in Chapter 3. This is just a matrix, okay? It's a matrix A minus a matrix that has lambda down where the ones would abandon the identity, and you could subtract them. So think of this as just like some matrix. Okay, if we have a matrix times a vector and it equals 0, one solution, the trivial solution, is if all the vector's components were 0. Okay, if there's not a unique solution, if there is a unique solution, it's all the components are 0. If there's more than that unique solution, what do I know about the determinant of this matrix right here? So we're going to be using Chapter 3 stuff all the way through this, why we learned about determinants. If I want this stands for a system of equations to solve equaling 0, and I want there to be more than just one solution of 0, 0, 0, 0, what would I need to know about the determinant of that matrix then? So if I want to get more solutions than one, what does the determinant of the coefficient matrix need to be? Trying to help you make some connections with Chapter 3. Anybody? Brave? Okay. Not 0. Okay. Or I heard, what's that? Okay, actually I got not 0 both times. Well, let's think about it for a minute. If the determinant is not 0, that's when it meant it had a unique solution. I've got you a solution here. It's all zeros. But I want to know when it's not unique, when there's more solutions. So I don't want the determinant to be non-zero, because if it was not zero, it means there's only one answer. So remember, one of the things the determinant told us, if the determinant was zero, then homogeneous, we know there's infinitely many solutions. Okay, so I'm interested in where the determinant is zero. So you guys see that said not zero, and you weren't the only ones. Everybody, a lot of you were thinking that. But remember, determinant. System of equations, determinant of the coefficient matrix is not zero. You have a unique solution, meaning one answer. In this case, that would be the zero answer then. But if you want more than one solution besides the trivial solution on a homogeneous, the determinant has to be zero. So we're going to use that and put that determinant equals zero. And this is going to be a key to finding the eigenvectors, eigenvalues, and eigenvectors. If I can figure out the determinant of this matrix, figure out what lambda needs to be to make it zero, I will have the eigenvalues. Okay, so this is called the characteristic equation of A. We had characteristic equations for differential equations for the roots. Well, this is called the characteristic equation of a matrix, and it's going to be a polynomial with lambda in it instead of x. And so it's called the characteristic polynomial of A. And it's going to be the thing I use to find these eigenvalues, and then after the eigenvalues to be able to find the eigenvectors. So that's going to be important because we need to figure out when I could get another solution to this. Let's go back to the original ones we had here. Remember when we were looking at these and we found that there was two special ones where when you multiplied them by the matrix, you just scaled the vector. And one of those was this vector 2, 1. Okay, that was one that we found that when we did it, it just scaled it. So this is an eigenvector. It's one of the special ones. And what is the eigenvalue? The eigenvalue that goes with this, using the subscript lambda, because there's going to be two of them here. The eigenvalue that goes with this is, well, what did the vector get scaled by? So this is the transformation. If I rewrote this and factored a 2 out, I see that the vector got scaled by 2. It's twice as long. So that's the eigenvalue for that vector. So 2, 1 is the eigenvector, and the eigenvalue is 2 because when you multiply it by that matrix, it essentially scaled it by 2. All right, so if we took that other one we found that worked, this is the eigenvector. The eigenvalue is what? Eigenvalue is the value, what it got multiplied by, essentially when it got transformed. So
-3.
Yep, so that's the eigenvector, good, that corresponds with the the eigenvalue that corresponds with the eigenvector 1, -2. So when we could see them visually, we looked at a bunch till we found one that lined up. Well, you're going to be there all day if you're trying to do it that way. I mean, I had this planned out so that I knew which ones to use. But how did I find the ones to use? I didn't just sit and play all day. I knew how to find them. And so that's what we want to be able to know how to do. And once we do that, then this is going to apply to systems of differential equations for finding solutions in the end. So that's kind of where we're headed with this. All right, so how do we find them? Well, the answer to finding them was this. A minus lambda i's determinant has to be 0. So first of all, I've got to figure out what A minus lambda I is, and then I got to find its determinant, set it equal to 0. And we will have the characteristic equation that we need. So let's go ahead and do that. So what does lambda I look like? Well, the identity matrix looks like this for this matrix A, right? That's the identity matrix. It's the same size as A. if you took the identity matrix and you multiplied it by lambda, it means go in and multiply every element by lambda. Well, I can kind of cheat and use the same one here. I'll make those into lambdas now. This is what lambda I looks like. It doesn't matter what size your transformation matrix is as far as it's going to look like this, but the same size as your transformation matrix. So instead of ones down the main diagonal like the identity had, because you're multiplying it by lambda, it'll have lambdas down the main diagonal. And then what we want to do is we want to subtract those guys, okay? And after we subtract them, we're going to want a determinant. So let's subtract them first. Okay, you subtract component-wise, and so you do 1 minus lambda. So that's what we just got to write, 1 minus lambda, because there's not really any other way to combine those. And then you go to the 2 minus 0, and that's going to go right here. What's 2 minus 0 is 2. And then we do 2 minus 0 for the second row. And then we do negative 2 minus lambda for the second component in the second row. So what I just wrote down was A minus lambda I. It just simply, and notice what it does, it just subtracts lambdas down the main diagonal. All right, now to find the eigenvalues, I would take the determinant of that. So we want the determinant of 1 minus lambda, 2, 2, and minus 2 minus lambda. Okay, we know how to find that for 2 by 2s. So I do this one times this one. And remember, there are two terms, so you're going to have to FOIL. Oops, I wrote y, it's lambda. Okay, so that times that minus multiplying that 2 times 2 is 4. There's the determinant, and I want to know when that is 0. So let's FOIL this. I'm actually going to do last first because I want to write it in descending order. And lambda's like your x now. I'm going to have a polynomial with lambdas in it. So last times last is going to give me lambda squared. I'm doing it backwards. Okay, then we do outers and inners. And we've got negative lambda plus 2 lambda, so that's going to be plus lambda. And when we do first times first, that's going to give me 1 times negative 2 is going to give me negative 2, but I've also got this negative 4, so that's going to give me negative 6. Okay, so you FOIL that, combine with the negative 4. This is called your characteristic equation for this particular matrix. And if I can solve that for lambda, I will have the eigenvalues. All right, well, it factors. And I got lambda here, and we'll put 2 and 3. This one's got to be positive. This one's got to be negative. Now, this is the matrix that I showed you on the graph. So we already know the eigenvalues are 2 and negative 3, but this is how you would have found them if you didn't know that. This is how I found them when I went to make the slide. I just picked the matrix, I found the eigenvalues, and then I found eigenvectors, and then I transformed some others to show you first, and then I transformed those 2 to show you that they just scaled. So the first one is 2. The second eigenvalue is negative 3.
Is there going to be 2 for every 2 by 2 matrix, or like?
The answer is yes, but it will be repeated just like for any quadratic equation. You know, so you're going to get a quadratic when you do the determinant because you got lambda in 2 places on the diagonal, so those are going to get multiplied together. So that was a good question. You're basically quadratic for 2 by 2.
And with like 3 by 3, will you get 3 answers?
Yes.
Okay.
Because you're going to have 3 lambdas down the main diagonal. It's going to have 3. So the answer is yes. You're making some good connections. So you're going to get 2 eigenvalues for a 2 by 2. This is only going to work on on square matrices. You're going to get 3 on a 3 by 3. You'd get 4 on a 4 by 4, and so forth. Yes, that's exactly right. Because you're going to have lambdas down the main diagonal, and that'll generate a lambda cubed. or if you had a 3 by 3. So that was a good question. Any other questions? Okay, so this is how you find the eigenvalue. It's not too hard for a 2 by 2. You find a minus lambda I and take the determinant, put it equal to 0. Simplify it. You're going to have a quadratic polynomial with lambda for the variable. You're going to factor or quadratic formula if you have to. A lot of times they set them up so they're going to factor for you. And you've got your eigenvalues. Okay? So how do we find the eigenvectors? All right, so here was our 2 eigenvalues. And the eigenvectors were the vectors that when we multiplied them by a minus lambda I, we got 0. I mean, that's how we built this thing. So that's got to be true. So let's figure out what a minus lambda I is for each eigenvalue, and then we're going to solve the system of when it would equal 0 to figure out what vectors it is. So let's do that for 2. First of all, we're going to write down a minus lambda I, okay, and our lambda is going to be 2. So here's our original matrix. If you did a minus lambda I, this is a minus lambda I now. I just changed it. Okay, what it does when you do a minus lambda I is you end up subtracting lambdas down the main diagonal. So that's what this matrix looks like. 1 minus lambda, 2, 2, minus 2, minus lambda. Okay, but now we're going to look at it for lambda equaling 2. We're going to do it for the first eigenvalue. So put a 2 in there. So we're putting a 2 in right here. And we're putting a 2 in right here. So 1 minus 2 is minus 1. Still got the 2. Still got the other 2. Minus 2 minus 2 is minus 4. Okay, so that's what a minus lambda I looks like. That's this piece right here. Well, I want to solve and find the v's that make that equal 0, and that's a 0 matrix or 0 vector there. All right, so what would we do? We would take our a minus lambda I matrix, which is this one for eigenvalue of 2, and figure out when it equals the 0 vector. So again, we're talking row operations. You can see that these rows are multiples of each other. If I did negative row 1, I would have 1, negative 2, and 0. And then if I did 2 of that row 1 plus row 2, and I'm using the row 1 over here. So 2 times that added to that is 0. 2 times that's 4 added to that, 0, and 0. So there's my RRES for that one. Important. If you don't get a row of zeros, you screwed up, because we found a place where the determinant was 0, which meant it was a dependent system. So a dependent system, we're going to get a row of zeros. Okay, if you don't get a row of zeros in your RES, go back and find your algebraic mistake in your row operations. Okay, so you need to get a row of zeros or something's not right. All right, so V2 is free. Okay, V1 is 2 times that. So eigenvectors are these guys. There's more than one eigenvector, but we want the simplest one or easiest one to use. So if I factored the t out here to get one of them, this is the one I get. Now, if you we went back to the other slide, that was one of those special vectors that got transformed. I'm just going to go back there really quick. That was my first one right there. 2, 1. That vector was one that got scaled by this transformation, not rotated and stuff. So I found that first eigenvector. And so how did I find that first eigenvector? I found it by just taking a minus lambda I, augmenting it with zeros, and solving and expressing the solution. And I just need So any scalar multiple of that is also an eigenvector, but we just typically want an easy one to work with, so we would use 2, 1. That would be fine. Any question on how we found it? Hang in there another just few minutes. Let's see if you can find it for this guy. So I want you to see if you can do that same process and find me the eigenvector that corresponds with the eigenvalue of -3. You're going to take a minus lambda I and put this -3 in for the lambda, and then you're going to augment it with zeros and solve it. So go ahead and be doing that. I see the ones you can see are working. Nice job. I'm going to write it up here, but I'm going to be quiet so you can be doing yours. Okay, when you get the point where you're deciding what your V1 and 2 are, see if you got the same thing that I got. If you have any questions, please ask. So I'm just going to point out a couple of things here. If I factored the t out, I would have -1/2 and 1. And that would be an eigenvector, but we got to use these things to solve systems of differential equations, and we don't like fractions. It's just harder to work with. So an equivalent thing, what if I instead factored out -1/2 t, and if I did that, that would leave a 1, and this one would leave a -2. And that would be a ton easier to work with than the first one. So that's what we're going to do. If we get fractions in there, we're going to factor it out. Typically, kind of a general rule of thumb is you try and get this first guy to be a 1. So you factor out whatever's with the t, get the first guy to be a 1. That is if it leaves the other guys not fractions. You may want to factor out something else out of it as well, if the other ones are going to be fractions. And we'll see an example of that, so I'll show you. And it's not like an absolute must. It's just that we got to use these and multiply them by stuff, and who wants to multiply and add fractions? It's not very fun. So that's why we're going to do that. Any multiple of that would work. Now that's the other guy I had. That's the one that I found that when I scaled it, or when I transformed it, it scaled it by -3. So the vector is 1, -2, and by the time I transform it, it's going to be -3, 6. Any questions? That's a good example of how to find them in an easy one. I have well, we've got enough time. Not really. Okay, I wanted to show you how to do a 3x3. We learned pretty much the big idea from this section, and that's how to find eigenvalues and eigenvectors. But they are going to be a little harder if they're 3x3s, and I wanted to do a couple examples of that and just show you some things that might go on. And I'm not going to do that until Wednesday. Oops, I didn't mean to go forward with it because I'm not going to do it until Wednesday. Let me go back. Because we don't have enough time, and you've had a lot. You had a lot to sit there for 2 hours in front of your screen, whether it's your tablet or your computer. I hope you're not on a phone, but you have better eyes than me. Anyway, so let's call it good for now. You should have 5.1 homework done and submitted by tonight, as long with your test analysis. And I will be monitoring for questions, happy to answer them. And I also am going to be on tomorrow morning at 10 o'clock, our normal class time on Tuesday, to help you answer any homework questions. On this one, this 5.2 and or finding eigenvalues and vectors, but we're not done with 5.3, so I'll adjust the homework due date. But we'll finish 5.3 on Wednesday, and then we'll start 6 and done with linear algebra. So, any questions before we go? Background noise playing around here, somebody, but that's all right. We're done. No questions? Okay. I will see you on either C is in quotes, either tomorrow morning at 10 if you'd like some extra help with the stuff we've done, or Wednesday morning at 10.
Thank you.
Yep, question. And I'll hang around for whoever has some things now, but I'm going to stop the recording just a minute. Okay, let's see. Okay, oh, sorry, question. The chapter 4 homework, you just want the cover sheet or a PDF of all the problems. Okay, for chapters 3 and 4, I just want the cover sheet. That's all. I'm just making it simple for those 2 chapters because that's when all this started, and I'm just going, that's good enough for those chapters. Okay, let me get, I'm going to get a blank screen or blank PowerPoint so that I can write, and I'm happy to answer any questions. You get awesome. Just trying to get up a blank PowerPoint, and then I'm happy to answer questions. Anybody hung around? Somebody had a question. We were going to answer it after, so let me see your PowerPoint. Unless they didn't remember to stay. Looks like, Derek, you're the only one out there. Did you have a question? No?